Hello, so this is the lecture 5B. Here we shall first prove the Kronecker-Kapolei theorem. So what is the Kronecker-Kapolei theorem? A system of linear equations Ax equal to B has a solution if and only if the rank of the associated matrix equals the rank of the augmented matrix. Well, this is called the Kronecker-Kapolei theorem. There is only one book which I have read which calls it the Kronecker-Kapolei theorem. That's a book by Shillow, Georgie E. Shillow, G.E. Shillow. The title of the book is Linear Algebra. So I just call it the Kronecker-Kapolei theorem. Proof is very simple. Assume that the system of equations has a solution. Let C1, C2, Cn, the column vector, be a solution. That means that A, the matrix A applied to C1, C2, Cn is B. But what is the column vector C1, C2, Cn? It is C1 times E1 cap plus C2 times E2 cap plus plus Cn times En cap. So let us substitute this into the equation. It is supposed to be satisfied. So C1 times AE1 cap plus C2 times AE2 cap plus plus Cn times AEN cap equal to B. But what is AE1 cap, the first column of A? What is AE2 cap, the second column of A? And so on. So what do we get? C1 times the first column plus C2 times the second column plus plus Cn times the nth column is B, which means B is a linear combination of the columns of A. That means that B is in the linear span of the columns of A. So B is already in the column space of A, and so the column space of A and the column space of A augmented with B are the same. So the dimension of the column space of A equals the dimension of the column space of the augmented matrix. In other words, the column rank of A equals the column rank of the augmented matrix. That is, the rank of A is the same as the rank of the augmented matrix. So that's one direction. Converse is equally easy. Conversely, suppose that the rank of A equals the rank of the augmented matrix. That means that augmenting the columns by adding one more column doesn't change the column space. The column rank of A is the same as the column rank of A augmented with. That means after augmentation, the column space doesn't become larger. So the last column is already in the column space of A. The last column is in the column space of A means what? The last column B, the augmented column, that is, the augmented column is a linear combination of the columns of the matrix A. In other words, B is C1 times column 1 plus C2 times column 2 plus Cn times column n for certain scalars C1, C2, Cn. But column 1 is AE1 cap, column 2 is AE2 cap, column n is AEN cap. So B must be C1 AE1 cap plus C2 AE2 cap plus plus Cn AEN cap, or B is A times C1 E1 plus C2 E2 plus Cn En, or B equal to A times the column matrix, the column vector C1 C2 Cn, or in other words, C1 C2 Cn is a solution of the system. The system has a solution if and only if the rank of the augmented matrix and the rank of the associated matrix are exactly equal. And that completes the proof of the Kronecker-Kapolei theorem. And now we will take up the next important notion, and that is of the nullity, the null space of a matrix and the nullity of a matrix. So let us again start with the M cross N matrix A. Let us start with an M cross N, M rows, N columns. What is the null space of A? Null space of A is a set of all elements in Rn. Remember, elements in Rn are regarded as columns. All the columns with n entries V such that AV equal to 0. This is called the null space of A. It is simply those vectors which are nullified by A, which are annihilated by A. So the null space is obviously a vector subspace of Rn. Well, because if AV1 is 0 and AV2 is 0, add them up. A times V1 plus V2 is 0. So V1 is in the null space, V2 is the null space, implies V1 plus V2 is also in the null space. Similarly for scalar multiplication, so we can check that the null space is definitely a vector subspace. Obviously the 0 vector is in the null space. A into 0 is 0. So 0 vector is already in the null space. So it's a non-empty subset and it is closed under vector addition and multiplication by scalars, and so it's a vector subspace. And so once it's a vector subspace of Rn, what is its dimension? The dimension of the null space of A is called the nullity of A. The dimension of the null space of A is called the nullity of A. And an important theorem, a very important theorem in linear algebra, which is going to be used several times, is a rank nullity theorem. What is the rank nullity theorem? Rank nullity theorem says that the rank of A plus nullity of A adds up to give you n, which is the number of columns. Proof will be taken up later. In every book on linear algebra will have a proof of this theorem. So we will take it up if time permits. For now, we will assume it. So now let us now look at the structure of the space of solutions. Now you want to look at the system of equations Ax equal to B. Of course, if the system has no solutions, then the space of solution is empty and there's nothing more to say. So assume that the system, the more interesting case where the system has a solution x0. The system of equations has a solution x0. I want to know what are all the solutions. System as a solution basically means that by the Kronecker Kapolei theorem, rank of A is the same as rank of A augmented with B. All right. The next theorem will tell you how to obtain all the solutions if you know one single solution. So if you know that one single solution x0 exists, and if you know this solution, then you can determine all the other solutions. How? Simply add to this specific solution all possible elements in the null space. Add to this specific x0, you have caught hold of one solution x0, and you keep on adding n, where n varies over the null space, and you will get all the solutions. Let's prove this. Let S be the set of all solutions of Ax equal to B. Okay, and let T be the set displayed in star. That is, T is basically the set x0 plus n, where n belongs to the null space of A. We want to show that S and T are equal. All right. So let us take an element of T and let us see whether that satisfies the equation. A of x0 plus n is Ax0 plus An, but n is null space, so An is 0. So that goes away. So you got Ax0 and Ax0 is B, because x0 by definition is a solution. So certainly x0 plus n is also a solution. So x0 plus n belongs to T implies x0 plus n belongs to S. So T is a subset of S. In the reverse direction, we want to show that S is a subset of T. So let us take an element x in S. It's a solution of the system of equations. That means Ax equal to B. But we already know Ax0 equals B. So we must take the difference. We take the difference, subtract. A times x minus x0 is 0. Which means x minus x0 is in the null space of A. Call x minus x0 as n, which means that x is x0 plus n, and x0 plus n is in T, because x0 is the given solution, the specific solution, the known solution, and n is an arbitrary element in the null space. So and that's how you get your T. So your x0 plus n will land up in T, and so S is contained in T. Therefore, the two sets are equal. So now you know this. So you know exactly this solution set. Now let us ask ourselves this question: when will this solution or the system of equation be unique? We are assuming that the system has a solution. Okay, so we are assuming that the solution exists. The solution exists. We want to know whether or not it is unique. When will it be unique? The solution is unique means this set of solutions must be a singleton. When will the set of solutions be a singleton? We already know x0 is in the solution set. The only way in which this set x0 plus n such that n belongs to null space. Only way that set reduces to a singleton is if the null space contains only the zero vector. Null space containing only the zero vector means the dimension of the null space is zero. That means the nullity is zero. So the solution of the system of equations has, so if you know that the solution exists and if the nullity is positive, the system has infinitely many solutions. If you know that the solution exists and the nullity is zero, then the system has a unique solution. Of course, so in case the nullity is bigger than zero, the system either has infinitely many solutions. If it has a solution at all, then it must have infinitely many solutions, or it may not have a solution at all. If the Kronecker, if the hypothesis rank of A equal to rank of A augmented with B fails, then it may not have a solution. Similarly, if the nullity of A is zero, the system will have a unique, if at all a system has a solution, it will be unique, or the system may not have a solution. If again, if the rank condition fails, the rank of A equals rank of A augmented with B, if that fails, no solution. If that holds, then unique solution, provided the nullity is zero. So this is the structure of the solution. Now let us look at this theorem. Let us give a geometrical interpretation of this theorem. Let us look at a simple, almost trivial example. I'm going to take a 1/2 matrix. I'm going to look at one equation in two variables. What is that equation? 2x minus y equal to 4. 2x minus y equal to 4. What is that? That's a line in the plane, right? That's a line sitting in the plane. What is the null space? The null space is all those vectors xy such that 2x minus y is 0. All those vectors xy such that 2x minus y equal to 0 is a line passing through the origin with slope 2. And that line has been drawn in red ink. And we have one solution of this system of equations. I'll put y equal to 0 and I'll take x equal to 2. So 2 comma 0, the point P, which is 2 comma 0, is certainly a solution. What does the theorem say? To get a general solution, to get the general solution, I have to add to this P every element in the red line. So what is the typical element of the red line? It is a line with slope 2. So it is t comma 2t. So I must add t comma 2t and I must add to this specific solution 2 comma 0. And you'll use the parallelogram law of vector addition, and here is where you'll see n plus p. So as n varies over the red line, this n plus p will vary over the blue line. And so this blue line is a solution set. In other words, the solution set is the null space translated, the null space translated by a specific known solution. Null space translated by a specific known solution. So that's a structure of solution. You will actually see a similar theorem for differential equations in the second half of this course, MA108. A very similar situation will occur when you solve differential equations, linear differential equations, the structure of solutions. And the null space will be called the complementary function over there. And the special solution will be called a particular integral. And the general solution is a particular solution plus the general solution of the homogeneous system. That is when B is 0. So you'll return to this in MA108. Now let us look at a simple example. Again, a geometrical example. Let us consider three planes in R3. A1x plus A2y plus A3z equal to D1. B1x plus B2y plus B3z equal to D2. C1x plus C2y plus C3z equal to D3. Three equations inhomogeneous. That is, there is right hand side. I can write it as a system of linear equations. Right? Ax equal to B, where A is a 3x3 matrix, A1, A2, A3, B1, B2, B3, C1, C2, C3, and B is a column vector, D1, D2, D3. And so now I'm telling you, so now what happens is that you got three planes in R3. What are the possible geometrical configurations of three planes in R3? The three planes could be parallel, or two of the planes could be parallel and the third could meet it transversely. The three planes may meet at a unique point, like the three coordinate planes, no? XY plane, YZ plane, ZX plane. They meet at a unique point, such a situation. The three planes may pass through a line, like 3 pages of a book. Or the three planes may form a prism. Are there any other configurations? Please discuss amongst yourselves and argue out your case. So now I'm going to tell you, I find that the rank of A is 2, and I find that the rank of A augmented with B happens to be 3. What's the first conclusion you're going to draw from this? The Kronecker-Kapolei theorem says that the system of equations does not have a solution because the rank of the associated matrix is 2, the rank of the augmented matrix is 3. The system does not have a solution. So definitely the three planes cannot have a common point. So some of these configurations are out. Okay. Can the three planes be parallel? The three planes are parallel, then the rank of A must be 1, right? So parallel business is over. So which configuration is it? Maybe it is 2 of them are parallel and the third one intersecting it transversely. All the three planes passing through a prism. So how do you decide which of these 2 configurations is the correct configuration? The rank alone doesn't tell you that, because the rank of a matrix can be 2. You've got a 3 by 3 matrix A. A is a 3 by 3 matrix, and I'm saying that the rank is 2. The rank could be 2 for 2 different reasons. The rank can be 2 for 2 different reasons. Reason number 1, the first 2 rows are proportional. The second row is a multiple of the first row. Or no 2 rows are proportional and yet all 3 rows are linearly dependent. V1, V2, V1 and V2 are not collinear. V2, V3 are not collinear. V3, V1 are not collinear. But V2, V1, V2, V3, all 3 taken together are linearly dependent. So there are 2 different reasons how the rank of a 3 by 3 matrix can be 2. So now you can use that to decide which are the configurations, what will be the corresponding geometrical configurations. Okay, so that is that. And that's a nice geometrical example. We will do some, we got these tutorial problem banks where you will see large number of numerical examples. A very nice thing I want to tell you that there is this book by Shom series, Shom's Outline. I mean, there is Shom series for a variety of different subjects, and Shom series for linear algebra is very good. It's very good. It has got a large number of problems, solved and unsolved. Illustrated problems are there, and large number of unsolved problems are also there. You can try your hand. I mean, you have a gold mine of problems in Shom series at varying levels of difficulty. So you take your pick. So that is one book I would like to recommend. Another book which is very nice is a book by Hurston and Winter, Linear Algebra and Matrix Theory. That's also a very user-friendly book. You can take that. That also has a large number of problems. The Shom series has a wealth of exercises, solved and unsolved, both. So you can try that. So after this little exercise in geometrical exercise, let us now go to the next little more theory. Determinantal rank. Now I'm going to assume that you know the basic properties of determinants. You don't have to know the whole theory of the determinant in great detail. What you really need is the following from the theory of determinants. Determinant of A equal to determinant of A transpose. That you need. What happens to a determinant when you switch 2 rows? The determinant changes sign. If you add a given row to any other row, the determinant doesn't change its value. Multiplying a given row by some lambda has the effect of multiplying the determinant by lambda. You know these 3 properties, you use them a lot. You know them for 3 by 3 matrices, 3 by 3 determinants, but these rules hold for determinant n by n determinant. Okay, this is all that you really need. And one more result you need is determinant of A equal to determinant of A transpose. This is not altogether obvious. This is slightly non-trivial. But if you have developed enough linear algebra to be able to prove this at this stage. The proof is not completely trivial, but the proof is not difficult. It's perhaps slightly lengthy. You need to think through and organize your the arguments. But we will assume this for now. If you have the steam, you can try to do this by yourself. So let us begin with a simple lemma. What is the lemma? Suppose A is an n cross n matrix. A is an n cross n matrix, and you are going to take a k cross k submatrix. I'm going to take a k cross k submatrix, and this k cross k submatrix has non-zero determinant, and the rank of A must be at least k. Conversely, if the rank of A is at least k, then there must be some k by k submatrix with non-zero determinant. The lemma is not difficult to prove. Let us see how to prove the lemma. First, we'll begin with a simple observation. Now, suppose I give you k column vectors. C1, C2, Ck are k columns which are linearly independent. They're linearly independent. Now, what I'm going to make is that I'm going to enlarge these columns. I'm going to put some more things under the C1. I'm going to put more things under C2. I'm going to put more things under CK. I'm going to make C1 D1, C2 D2, CK DK, where D1 is another column. Of course, there is the sizes of these matrices must be the same. So C1 D1 is a larger column. C2 D2 is a larger column. But all these columns are the same size. Now, what I'm saying is that if C1, C2, Ck are linearly independent, then these are also linearly independent. That is, if I increase the size of the columns, it's still going to be linearly independent. Are you convinced? Suppose there exist scalars A1, A2, AK. So A1 times C1 D1 plus A2 times C2 D2 plus AK times CK DK is 0. Then in particular, that would mean A1 C1 plus A2 C2 plus AK CK is 0. But C1 C2 CK are given to be linearly independent. So A1 A2 AK must be 0. So that's what we wanted to prove. Alright. So now let us assume that A0 is a k by k submatrix of A. And determinant of A0 is 0. Determinant of A0 is non-zero. Determinant of A0 is non-zero. Determinant of A0 is non-zero. Remember that if the determinant is non-zero, then the columns are linearly independent. So columns of A0 are linearly independent. But remember that what is A0? A0 is a submatrix. So the columns of A0 are basically parts of columns of A, isn't that so? So columns of A0 are Ci1, Ci2, Cik. But the corresponding columns in A are Ci1 tilde, Ci2 tilde, Cik tilde. But Ci1, Ci2, Cik are already linearly independent, and we know that we have linearly independent columns. I make the columns longer. If I enlarge the columns, the enlarged ones will also be linearly independent. So k columns of A, the taller columns of A, are linearly independent. So the column rank of A is at least k, but the column rank is the same as the row rank, and that common value is called the rank. So one part of that has been proved. Conversely, suppose that the rank of A is bigger than or equal to k. That means that A must have at least k linearly independent columns. Okay, A must have k linearly independent columns. So I just select these columns. I select these columns and consider the submatrix. How many columns have I selected? K columns. How many rows are there? M rows. So these k columns will form a M cross k submatrix B. So B is obtained from A just by keeping those k columns and discarding everything else. How many linearly independent columns does B have? K. So what is the rank of B? K. What is the column rank of B? K. What is the rank of B? K. But column rank of B is the same as row rank of B, isn't it? So rank of A, which is greater than or equal to K, K is the rank of B. K is the column rank of B, but the column rank of B is the same as row rank of B. B is a M cross K submatrix. But now, since the row rank of B is K, k rows of B must be linearly independent. Select these k rows. Remember, B is a M cross K matrix. B has M rows and K columns, but I'm going to knock off all the rows and only keep K rows. What am I going to get? I'm going to get a K by K submatrix. I'm going to get a square matrix C of size K by K. But which rows have I kept in B? The linearly independent ones. The K linearly independent rows I have kept, and the rest I have thrown away. But if the row, that means that the rows of C are linearly independent. But the determinant of C is not 0. And so this C is the desired K by K submatrix. Okay. So we have proved a very important lemma. If the rank of an n cross n matrix is at least K, then some K by K submatrix must have non-zero determinant. Conversely, if a K by K submatrix has non-zero determinant, the rank must be at least K. Now let us go to the next. Now, how do I use this lemma? The lemma, let us now think about this. So now I'm giving you a matrix A. I'm giving you a M cross N matrix A. And now I'm going to say that the rank of A is exactly K. I'm going to say that the rank of A is exactly K. Which means that by this lemma, there must be a K by K submatrix with non-zero determinant. I'm saying that the rank of A is exactly K. So by the first clause in the lemma, there must be a K by K submatrix which has non-zero determinant. Now, I take any K plus 1 by K plus 1 submatrix. I know there's a K by K submatrix which is non-zero determinant. What about K plus 1 by K plus 1? Suppose a K plus 1 by K plus 1 matrix also has a non-zero determinant, then the second clause will tell you that the rank must be greater than or equal to K plus 1, no? Suppose that some K plus 1 by K plus 1 submatrix is also non-zero determinant. The second clause will immediately tell you that the rank cannot be K, it must be at least K plus 1. But I told you that the rank is exactly K. I told you that the rank is exactly K. So what's the story now? Putting these two pieces together. If the rank of a matrix is exactly K, then there must be at least one K by K submatrix with non-zero determinant, and all K plus 1 by K plus 1 matrices, submatrices must have zero determinant. That's very interesting, because now I'm going to say that suppose A is an n cross n matrix with the property that some K by K submatrix has non-zero determinant, and all K plus 1 by K plus 1 submatrices have zero determinant. Then the rank of A must be exactly K. This idea of talking about rank in terms of determinants is called the determinantal rank. This is called the determinantal rank. In fact, if you read books written in the first half of the 20th century, you will see that determinants are more prevalent, and determinantal rank via determinants is more prevalent. It's a more prevalent discussion. Gradually things have changed, but the determinant rank is also important, but it doesn't occupy the same distinguished position now as it used to earlier. Also is my opinion. So what is the determinantal rank? You say that a matrix A has determinantal rank K if there is some K by K submatrix which has non-zero determinant, and all K plus 1 by K plus 1 matrices, submatrices have zero determinant. We have just seen that the determinantal rank is the same as the column rank, is the same as row rank. If the column rank is A, which is the rank of the matrix is A, that means the lemma tells you that there's a K by K submatrix with non-zero determinant. Now, if there's a K plus 1 by K plus 1 submatrix with a non-zero determinant, then the lemma will also say that the rank is at least K plus 1, and that's a contradiction. So all K plus 1 by K plus 1 submatrices have zero determinant. That completes the discussion of the determinantal rank. So you got row rank equal to column rank equal to the determinant rank. There are three different ways of thinking about the rank, but they all are the same. They cough out the same number, and that is important. Now, in the next slide, you will see a nice example. I given you a 2 by 4 matrix A, and I'm going to calculate AA transpose, and I'm going to calculate A transpose A. I want you to tell me what is the rank of AA transpose, and I want you to tell me what is the rank of A transpose A without multiplying the matrices out. First of all, can you tell me the rows of A? Are the rows of A linearly dependent? Is the second row a multiple of the first row? No. Is the first row a multiple of the second row? No. So the two rows of A are linearly independent. So the rank of A is straight away 2. So let us call the first row V and the second row W. So V and W are linearly independent vectors in R4. So remember I told you the gram determinant V dot V, V dot W, W dot V and W dot W. That must be non-zero. The determinant is non-zero. But that matrix is exactly AA transpose. So straight away rank of AA transpose is also 2. Now I want to understand what is the rank of A transpose A, and you look at this slide and we'll talk about this next time, and that completes lecture 5.